Today I'm fortunate to be joined by Xanda Schofield, an assistant professor at Harvey Mudd College. So you work on topic models?
That's right. I want to make topic models easier to use for humanists and social scientists for understanding large text data sets.
A worthy goal? My first degree was in history. Why would they need topic models? Isn't a search engine enough?
A search engine is a good comparison. If you know what you're looking for, a well-indexed search engine works great. Type in the right keywords and you'll find the documents that you're looking for, but if you don't have a specific thing you're searching for, it can be useful to start from somewhere more basic, finding out which words show up together. When things work well, we can find patterns of co-occurring words that match concepts a historian might care about, and then help them use quantified versions of those patterns to help make sense of the corpus.
Okay, so if search engines can find a needle in a haystack, what are some examples of how people have used topic models to tell the story of a haystack?
Oh, there are loads. Early examples, when topic models first started out, often centered discovering different research subtopics in scientific papers, but nowadays they're used for things as broad as finding imagery words that arise together in poetry, so that's work from Lisa Rohde, or understanding how people find out information about healthcare in online search queries, which is a piece of work from Maria de Bebe. Sometimes we even change things up by replacing this concept of words in documents, like we would usually use in an NLP, with things that have the same countable structure, like songs on playlists, items in online shops, or artifacts discovered in different rooms in an archaeological dig site.
Topic models, as you'll see in a second, are built on a purely probabilistic formalism. This was what was popular in the early 2000s before everyone saw the light and switched to neural models. Why are people still clinging to these old-fashioned models?
I get this question a lot. Why still bother with topic models? It turns out that with neural models, it's often hard to see how parameters connect to what the models infer, as well as why the inference does or doesn't make sense. As hopefully will make sense soon, probabilistic models give parameters that have a more concrete meaning, related to proportions and probability, so they can tell a clearer story, something especially helpful in cross-disciplinary work.
Why is that? It's all just matrix multiplication and continuous differentiable functions. What's unclear with that?
There's a particular magic to the way probabilistic models tell a generative story, a fictional version of how text gets written that we can pick apart. For instance, we say that we have a fixed number of topics that are distributions over words, and each of our documents has a distribution over topics. In our fictional universe, each document is written by randomly sampling a topic from our document topic distribution, then sampling a word from that topic's distribution. You can rinse and repeat until you have all the words in your text.
But it's quite obvious that the model is wrong. It's not how an author would actually sit down to write a document.
There's a famous statistics adage, which I consider the live, laugh, love of the statistics world. All models are wrong, but some models are useful. Topic models make a very wrong simplifying assumption about text, but the simplicity of that assumption and how well it works in practice to fit a lot of text turns out to be very useful.
Okay, let's say that I wanted to use topic models. How would I actually go about doing that?
Honestly, you'd likely go to an existing implementation of some standard topic models. Mallet for smaller medium data sets, or maybe Jensen or PyTorch for really large data sets.
What if I wanted to develop my own new topic model?
Then we're going to get into the nitty-gritty of how to set up model inference. In particular, for topic models, our generative story doesn't give us an objective that we can solve for directly. Just like with neural nets, though, we have iterative ways of finding good solutions anyways. There are two broad ways of optimizing topic models' objective functions: Gibbs sampling and variational inference.
We'll talk about both of these. What are the advantages and disadvantages of these?
Gibbs samplers tend to be faster to develop and run. However, because they use sampling to find a solution, it's harder to track when the model converges.
Okay, and what about variational inference, the other option?
Variational inference is easy to parallelize, so if you have a big compute cluster, it might make more sense. And it is more compatible with automatic optimization like you see in PyTorch, because the parameter updates it does more directly signal convergence. That said, for a model with lots of parameters, in practice sometimes it converges a little too readily to a less than awesome local optimum, where a sampling approach has less of that problem.
I've heard about variational autoencoders. Does that have anything to do with variational inference?
Yeah, at a high level, they're both trying to find a representation that explains the data. More mathematically, they're using Kullback-Leibler divergence to measure how far apart a variational distribution is from a real distribution.
But these topic models are just simple distributions. What if I only care about neural networks?
If you wanted, you could define a distribution using a neural network and then use the KL divergence-based objective, we'd call it a variational objective, to find the weights of the network that best describe your data.
But why are we talking about these probabilistic models? When are we going to get to the good stuff?
The nice thing about starting with variational inference is that it's easier to get your head around than neural networks. So you can understand what the variational objective is doing before we get to the crazy multi-layer networks.
Sounds good. Let's now find out what topic models are.
If you want to see more videos like this, check the video description for the course that comes from the link down below. You can then see the context and the correct order for watching these videos. YouTube will gleefully show you stuff in the wrong order. If you want other people to see this video, provide a big gradient to the recommendation algorithm by clicking the like and subscribe button down below.